right, class, good morning. Happy Saturday. We've got the videos working again. This is so exciting. I was so happy I cried. So now I can get you guys the videos for chapter 2. So chapter 2 is going to be a little bit of a review of the last section in finite math, which covered logic. But we're going to be doing some new stuff with it. So stick around. So section 2.1 is all about truth table proofs. Now that's what we did in finite math. So this section should be a little bit of a refresher, which is always nice to have. So there are 4 different logical connectives, right, that we use to connect our statements. So we have conjunction that stands for and. Now in finite math, we used this symbol. In this text, he uses a dot. You can use either symbol. I personally don't care. It's up to you. So do whatever makes you not get confused. We've also got disjunction, that's or. We've got negation, that's a tilde in this text. I think in the last text it was one of these. And then we have implication for if then. We did do a preliminary introduction into logic in chapter 1. If you aren't quite to this stage, go back and rewatch those videos. So truth tables are a tool that we use to prove the logical validity of a statement, okay? And the idea behind truth tables is to try all possible combinations of true and false values that a statement could have, and their possible combinations, to see if the question is true in all of the given appropriate situations. So remember, when I have a statement, here's a simple statement P. It could have 2 possible truth values. It could be either true or false. In logic, there's no gray areas. So we can list all the logical values of P in a table. Here's the truth table for not P. This is the negation of P. So here we have not P. It takes the truth value from true to false. A statement form that has a true value of true, regardless of our true values of our initial statements, is called a tautology. So that's a combined statement where we get everything is true. Friendly reminder that a contradiction is a statement form that has a false truth value, regardless of the truth values of our initial statements. Cool, refresher. Logical equivalence. We say that 2 statements are logically equivalent, okay, which we denote with 3 lines together, provided P is true precisely when Q is true, okay? That means they have the same truth value under any assignment. So a good example of that is the implication. So P implies Q, and then we've got not P or Q. So if I make this truth table, we see that these are both true at the same time and false at the same time. So I would say that these 2 statements, and I'd want to put them in parentheses just to double check, are logically equivalent. So demorgans laws are 2 laws that are a good example of logical equivalence. So these laws relate negation and conjunction and just disjunction. So if I have not P or Q, right, that's the same as not P and not Q. If I have not P and Q, that's the same as not P or not Q. This is an example of a rule of replacement. We're going to be talking about that a lot in sections 2.2 and 2.3. And friendly reminder that I'm using the new notation for and, but if you use the old notation on the homework, I'll understand what's going on. So let's go ahead and prove one of De Morgan's laws. Let's prove this first one. So let's make a truth table to prove that these 2 statements are logically equivalent. Maybe I should switch not to green. Okay, so if I have P is true, true, false, false, then Q would be true, false, right? This is so I have every possible combination of true and false. So this first column's not P. That's the negation of our P. So if P was true, now it's false. P was true, now it's false. True, true. I have to do the same thing for Q. Q was true, now it's false. True, false, true. Okay, so not P and Q. Remember P or Q, right? Remember P or Q is true if one or the other is true. So if I have true and true, that's going to give me a true value for P and Q, but it's not P and Q, so that gives me a false. If I have P or Q, I look over here and I've got a true and a false. That would give me a true truth value, but we have this negation outside, so again I have a false. If I have false and true, that's going to give me a true truth value for false or true, but then we negate it, so it'd be false. And then I've got false and false. That's the first time I'm going to get a false value for P or Q. Not false gives me a true. Next, I've got not P and not Q. You can note that with a little thing. Remember, and it has to be true for both of them. So I've got false and false, gives me a false. False and true, still false, because and is only true when both truth values are true. True and false gives me a false, and true gives me a true. So as we can see, both of these take on the same truth values given their different conditions. So they are logically equivalent. And one thing I did before we got the videos working was I included all the answers in the PowerPoint. So that's a nice step. Okay, let's go ahead and prove the other, De Morgan's other law. The logical equivalence of not P and Q gives us not P or Q. Don't know why we zoomed in right there. Let's switch back to blue. So we fill in the first two columns of our truth table, and those are our favorite because they never change. If I have not P, again, I've got false, false, true, true. And feel free to pause at any time and try and work this out for yourself before I continue on. Not Q is going to be false, true, true. So here I've got P and Q. Okay, that's only true when both P and Q are true. So if I look over here, I've got a true and a true. So that would give me a true and value, but remember this negation, so I've got a false. I probably should have made another column in my table for that, now that I'm thinking about it. I've got true and false. That's going to be false, but not false is true. False and true, that's going to give me a false, but not false is going to give me a true. And false would give me a false truth value, and not false would give me a true. Why are we zooming in so much today? Okay. Then I've got not P or not Q. Remember, it only has to be true for one of the values. So if I've got at false or false, that's still false. False or true is true. True or false is true. And true is true. So as we can see, these two statements are logically equivalent because they take on the same truth values given their starting initial conditions.